In this section, we will discuss basic SELinux security concepts. SELinux, or Security Enhanced Linux, is a mechanism of mandatory access controls. So far, what we have discussed is discretionary access controls. For example, every process on the system runs as a user and also has group credentials. When it tries to access any files, it will use those user and group credentials in order to determine whether it should use user group or other permissions for those files. Owners of the files have the ability to change the permissions on those files. Let's look at the web server. The Apache web server runs as the user and the group Apache. It needs to be able to read its content from the var www.html directory. It would also read its config files, and it would write to its log files. Since it runs as an ordinary user on the system, it also would have the privilege to both read and write to the /tmp folder. We can review this information from the command line as well. The ps command can show us that the user for HTTPD process is the user Apache. An ls-l of var www will show that the document root allows everyone to read and execute, including the user Apache, and that the content held within there, in this case an index.html that would be displayed as web content, is also readable by everybody. In my case, the web server can display it because of its group permissions as well. Unfortunately, this also means that the web server could display out the contents of other configuration files, including the etc password file, which is readable by everyone on the system. This is a configuration file which holds a list of users that are defined on this system. And since it is readable by the user Apache, it could be included amongst web content and displayed to users who are legitimately even watching the web page. This is known as accidental information leak on the system. In addition, if there's an exploit available and a malicious user compromises the system through the Apache service, they would end up on the system as the user Apache. By default, they would be able to read a number of configuration files, including our list of users on the system, and also be able to read and write to /tmp, thereby filling up the file system and causing other denial of service types of attacks. SELinux is a mandatory access control mechanism. It has a security administrator, in our case root by default, and it has a policy that controls access and permissions. As a mandatory access control policy, it cannot be overwritten by the users. In our case, it has a list of explicit allows, and the default is to not allow anything at all that has not been explicitly allowed. It can even be used to make our permissions more restrictive. Mandatory access controls come in a number of different formats. There are role-based access controls, multi-level security, and type enforcement, for example. SELinux could implement any of these. Red Hat Enterprise Linux implements SELinux with a policy that we call targeted that uses type enforcement. We call it targeted because our goal is to contain services, to target individual services and put them into their own container. So in our case, an SELinux enforcing mode on the web server would have explicit allow statements allowing Apache to read its content from var www.html. But without any explicit allows, the web server would not be able to interact with other files on the system. This includes config files like the password file, user data, and also the /tmp folder. By using type enforcement, what we do is we apply a label or a context to various objects on the system. Every file on the system gets a label or a context. Every process also gets a context. Users get a context at login. Even ports and network interfaces can be labeled. The policy then defines how the various labeled objects can interact with each other. The security admin, again root in our case by default, can change labels on files and can also make some minor changes to the policy because the policy is built with some if-then-else statements or booleans. So an administrator would have the ability, if the boolean was already defined, to say yes or no to allowing certain interactions. For example, whether Apache could read user home data or not is a Boolean that's defined in our policy. An administrator can choose whether or not to enable that particular privilege. The idea is to contain the service and only allow that service to interact with relevant objects, not allow it to interact with anything else. This means that someone who compromises the system becomes the user Apache, but instead of being able to get to any file that the user Apache has privilege to read or write to, it can only get to the objects that have the correct SELinux labels as well. Let's look at some sample labels. The ls command has a capital Z option that can be used to view the security context. This will show the discretionary access controls at the beginning, the owner and the group, and then a long string which is the SELinux context. This consists of a user, a role, a type, and a sensitivity. Since we're just doing type enforcement with the targeted policy, we're primarily interested in the third field here, which is the type. In my case, for the document root, this is httpd_sys_content_t. Most of the types that are used in the SELinux targeted policy end in an _t. If I look at the CGI bin directory, which would hold scripts for my web server, there's a slightly different context or type label associated with this. Processes also have a label, so if I add to my ps command to show the context, then I'm able to see the SELinux context. Our type here is an httpd_t type. What happens is that the policy then has an allow statement that allows the type httpd_t to read files which have the type httpd_sys_content_t. It also allows the httpd_t type to read and execute scripts which have the httpd sys script exec type, such as would be found in the CGI bin directory. On the other hand, the etc password file has a type of etc_t. With an SELinux policy, if it's not explicitly allowed, the interaction will be denied. By default, we do not allow httpd_t to interact in any way with the etc_t type. Therefore, the web server should not be able to read the etc password file. It would not be able to display its content amongst any content displayed to users. And if the system was compromised, a user with the Apache context of httpd_t would also not be able to access this file. Similarly, for the temp directory, it has a tmp_t type. And again, unless there's an explicit allow, the interaction would not be allowed. With SELinux permission errors, it's possible to be a little too restrictive. The enforcing mode is the default, but to help us with development and troubleshooting, there is also a permissive mode. The enforcing mode, as the name implies, loads the policy, labels all objects as needed, checks the policy. It also logs violations to the policy to the audit log, and ultimately only allows those interactions which are explicitly allowed within the policy. The permissive mode, on the other hand, will still label all of the objects, load the policy, check the policy, and log what would be denials to the audit log, but will ultimately permit all actions. This means that I can move to permissive mode, run through my application, collect the various logs entries that show what would be denied, and use that information to adjust my policy in order to be able to run my application the way that I want to, and also return to enforcing mode. This is also a great troubleshooting tool. If I'm having permission errors, I can move my system to permissive mode. If the errors all go away, then I probably do have an SELinux related configuration to change. If I go back to enforcing mode and my permission errors return, I get further verification of that. The security administrator, again root in our case, has the ability to change the context on files. It also has the ability to toggle the booleans to allow or disallow certain interactions, and a few other administrative capabilities for adjusting the SELinux policy. Once I get everything straightened out and I'm done with my troubleshooting, I should return my system to an enforcing mode in order to best protect that system. There is a third mode as well. There is a disabled mode. To switch into and out of the disabled mode, this is a kernel parameter, so I must reboot the system. In fact, when I return from disabled to one of the enabled enforcing or permissive modes, not only must the system be rebooted, when it does reboot, it will take some time to relabel all of the files on the system in order to be used. Again, the goal of the SELinux targeted policy, which uses type enforcement, is to protect our user data from our various system services. It's designed to contain the services within their own little world and set of types and minimize damage that might be occurred due to an exploit and a compromise of the system.